Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 6. Over and underdetermined systems of linear equations. In analyzing experimentally collected data, the number of equations is sometimes deliberately set higher than the number of unknowns in order to minimize the experimental errors. A linear system with more equations than unknowns is called an overdetermined system. In reality, such systems do not have exact solutions, but their solutions are obtained such that the approximate solution error is minimum. Another type of system of linear equations encountered in engineering is called an underdetermined system, where the number of unknowns is greater than the number of equations. Consider a system of linear equations with m unknowns, x's, and n equations. In such cases, n could be less than or greater than m. Or we may write the system in matrix form, where the A is an n by m rectangular matrix and B and x are vectors of length n and m, respectively. The residuals are written as follows. The goal of zero residuals cannot be realized. We minimize the objective function, i.e., the sum of the squares of the residuals, or the L2 norm square of the residual vector. To find the minimum, we set the partial derivatives of E with respect to the unknowns, x1 through xm, to 0. The result is a system of m linear equations with m unknowns. The resulting linear system of m equations and m unknowns can be expressed in matrix form as follows. If the determinant of the product of A transpose and A is non-zero, the direct solution can be obtained as follows. An underdetermined system of linear equations is one where there are more variables than equations, resulting in either infinitely many solutions or no solution at all. These types of systems are typically solved by finding the set of all possible, infinite, solutions as there is not a unique solution. The least squares method can also be employed to minimize the norm of the residual. It seeks a solution that is best in some sense, typically by minimizing some of the squares of the residuals, that is, L2 norm of the residual vector. If the system AX equals B is underdetermined, the least squares method will find the closest solution in the least squares sense. In case the determinant of the product of transpose matrix A and matrix A equals 0, the system is regularized by adding a regularization term to the objective function to ensure a unique solution. The solution is found by minimizing the objective function stated as follows. Where lambda is a small positive constant, referred to as regularization parameter, and the norm x is the L2 norm of the vector x. There are other methods, such as singular value decomposition, gradient descent, etc., that can tackle underdetermined systems, but they are not covered in the text. Consider a beam with 3 unknown forces, but we have 5 strain gauges to measure strain at different points. In other words, we have more measurements than unknowns, creating an overdetermined system. Determine the unknown forces if the system of equations based on these measurements is given as follows. The residuals can be expressed as follows. Then the sum of the squares of the residuals become. Now, taking the partial derivatives with respect to f1, f2, and f3 and setting to 0, we obtain the following 3 by 3 linear system, whose solution results in f1 equals 89.26, f2 equals 73.35, and f3 equals 32.82 newtons. The sum of the squares of residuals is found as 11.735 newtons. Alternatively, Using the matrix forms, the problem can be cast as AF equals B, where A is a 5 by 3 rectangular matrix, B is a vector of length 5 containing the right-hand side, and F is the vector of length 3 containing the unknowns. Upon employing the least squares, the reduced linear system becomes a 3 by 3 system of equations. Consider example 1 with 4 unknown forces and 3 strain gauges to measure strain at different points. In this case, we have more unknowns than measurements, leading to an underdetermined system. Determine the unknown forces if the system of equations based on these measurements is given as follows. Using the matrix forms, the problem can be cast as the matrix equation, AF equals B, where A is a 3 by 4 rectangular matrix containing the coefficients. B and F are the vectors containing the right-hand side and the unknowns, respectively. Upon applying the least squares procedure, the linear system becomes a 4 by 4 system of equations. However, the determinant of the coefficient matrix of this new system is 0. Since, specifically, the determinant of the matrix product of transpose A and matrix A is 0, we will regularize the system as follows, where lambda is the regularization parameter, and the coefficient matrix becomes a function of lambda, which should be set to a small number. When we solve the system for lambda equals 1, 0.1, and 0.01, we obtain the following solutions. We conclude this video session with the converged solution. That is all for now. See you next time with another topic. Bye.